Hey, maybe we should get started. It's 4 o'clock. So, yep, welcome everyone to lecture number 18 of CS 545, the introduction to robotics. And today we will be talking about sampling-based motion planning. The second lecture on that topic. So we had the first one on Monday, if you remember, although I used a different AI generated image for that. So today we have a newer image, which I think looks cooler. So, all right, logistical things. So your regrade request for the midterm are due Thursday, which is tomorrow at 11:59 p.m. So please try to make sure that you get all your regrade requests by that date. So it it's really going to be a little bit difficult if you ask me on Friday and come with a list of regrade requests and so on. So try to get it done by tomorrow night. And the way to do the regrade request is to show that, you wrote this answer is basically the same as the correct solution, but you didn't get all the full points, then that's the most effective regrade request. So, but the least effective one, I was in a hurry, I meant to say this, but, I wrote this, can you give me some extra points like that? That's less effective. So just be mindful if most of your regrade requests end up being like that. Yeah. Hi, homework 3 has been released and is due April 1st. Lab 3 has also been released. So again, for lab 3, try to get the simulation stuff done, and then you can book some time with the physical robot. So Shihan, and I believe is the lead TA, will be helping to coordinate with that. And the other TA, Hedja, will also be able to help with that too. Yeah, any logistical question? Yeah. So apparently, so I think what happened was maybe they just assumed we would use, like maybe I had to pick a day for the lab, but it turned out that we can just be much more flexible than that because there's lab space, but only one other class is using it. So there's a lot of flexibility in how we use the space. So look on Piazza for the sign up days. So apparently the whole Tuesday at 4 p.m. thing, like I think it's not happening. I think it's just going to be different days, and then just you pick among the days that we make available. Uh, anyway, I apologize for any confusion with the 2 days at 4. So I think we should just ignore those. Yeah, it's also my first time teaching, so for the next time I teach it, we're getting rid of that confusion. Uh, all right, other thing, other question? I'll give it a few seconds because there's a bunch of people who just got in. All right, so if there's no other question, we can dive into the sampling-based motion planning. All right, so it's a quick review for last class. So we gave an overview of an example type of sampling-based motion planning. So we talked about the roadmap-based method. So those are a class of algorithms. So again, whenever we talk about an algorithm here, just remember that there are many variants of these. So when you have something that's as simple as sampling, but you have many different parameters that you can tweak, you can probably assume that someone has tried that and then published a paper about it and so on. So, but the general idea behind the roadmap-based methods are: step 1, you build the roadmap. Step 2, you query it. And for these, you probably want to make sure you query it like multiple times to be a little more like efficient. Like it means if you're only querying it once, then you might as well just stick with the technique that we'll talk about later today. But if you have many queries to make, then maybe it's worth it to build a more complete roadmap first, and then you run all your many queries after that. So we talked about this probabilistic roadmaps and then this algorithm. So there's a lot of lines here, but most of it is like boilerplate stuff. You know, you make empty sets of vertices and edges. You have a bunch of sample points, and then you try to connect them with a local planner. So that's what remember what the delta means? So we have delta Q and Q prime, and then that's a local planner that can tell you like, can you go from Q to Q prime in without any collision. But again, this thing has to be simple enough so that you can actually use it many times. If it's really complicated and very sophisticated, you might as well just start with that as your planner instead of doing the whole sampling based stuff. And then, yeah, we talked about building this roadmap. And then whenever you have your starting point and then the ending point, you just try to connect them to any nearby node that's in the graph, and then you run your standard graph search algorithm. And then, so again, we were today and last class, we talked about the bunch of points, but just remember that the queue more broadly represents some configuration. So we only do it in 2D to make it easy to describe in a PowerPoint lecture. But if you're talking about like implementing it in practice, you would probably run it on like your 7 degree of freedom robot arm or whatever. So, but you can also think of these as like simple 2D robots that are moving on a plane. And then, and then this would be an appropriate abstraction. All right. All right, so again, the main issue with this is, step one could take a long time. So you might as well just think about, why don't we just build enough of this roadmap and then stop whenever we get the start to the end point. And so, for the most part, the hierarchy behind how we treat sampling-based methods are, those that are multi-query, like in last class, and then those that are single query for today. So you can, so if you're querying it multiple times, you can cache or more simply just store somewhere the roadmap and then use it for many times. And then for single query planning, you just recompute it for every query. And so the line between these is very blurry. So whenever we talk about things like, this is one class of algorithm, this is another class of algorithm, just remember that there's probably some kind of hybrid, or there's probably some kind of variant that includes the best of both worlds. In fact, that's often a subject of like many research papers that say, here's the benefit of this type of algorithm, here's the benefit of this other type, but they all have drawbacks. So how do you get the best of both while avoiding both drawbacks? Like that's a very common way to write a paper and to advertise your algorithm to people. So again, you can combine these. Maybe it's just not the best fit, but I mean, you can do whatever you feel like works. So. All right. So for today, the main new algorithm to know are the rapidly exploring random trees, or RRT, or RTF. Okay. So the algorithm is super simple. And I mean, if you look at the original paper, it's a 4-page technical report. And it turned out that like it's one of the most impactful technical reports I've ever seen. So yeah, based on like the number of paper citations and so on. So yeah. So again, imagine that we have our 2D setup, and then we have obstacles, which are this rectangle and then this triangle. So the algorithm for RT would be basically like how to build the tree. And then when you build the tree, it calls the subroutine extend RT. Yeah. So there's really like two main algorithms to look at. And again, a lot of this is like boilerplate stuff. You initialize something and then you do a for loop and so on. But let's look at how this works. So you have some input, which is Q0, the configuration where the tree is rooted. Yeah, maybe you just set it at random, maybe a prior knowledge, or whatever the case might be. And then you have some number of attempts to expand the tree. And the output is this tree, set of vertices and edges that is rooted at Q and has up to N configuration. So this time it's a tree, which means you don't have a cycle, which you might have in a roadmap. All right, so you start with one vertex, no edges, you iterate, pick a randomly chosen free configuration, you try to extend it, and then you repeat the process, and then you're done. Again, very, very simple. When you actually try to extend it, then if you're given your Q, it's a configuration where you're trying to get the tree to go to or to grow towards. I'm going to show videos of this later, so don't worry if this is like abstract. And then the output is going to be some kind of new configuration if you can expand the tree toward that free configuration, and it's going to be nil or basically nothing if it fails. So you find the closest neighbor, you progress towards that near point by the step size along the straight line between Q near and Q rand. And if it's collision free, you add it to the tree. If not, you just ignore it. Again, whenever we're talking about sampling-based algorithm, we always assume we can do some kind of fast collision checking. All right. So let's say we have some tree. We're at some iteration here. And QRAND is a randomly chosen free configuration. Like that. So this is our randomly chosen free configuration. So let's try to extend it. What's the closest neighbor of Q in T, which would be Q near? So the input, all right, so the input is Q rand. So that is what this Q means. So which point is Q near? Yeah, it's kind of hard to describe. You can't really point it because I can't tell where you're pointing, but it would be this one, right? Yeah. Yeah. So you pick that point. That's the closest neighbor of Q and T. Step 2 is you progress by the step size along the straight line in Q between them. Yeah. Right. And then this is assuming that the length of that line is the step size. Is it collision free? Okay, yeah, it's collision free. So you would add this to the tree, right? So just to be clear, you don't add this to the tree. You add this edge and then this vertex. So we're not adding this one edge. So all right, that's basically how the algorithm works. You continue that many times. Any questions? That's it. I mean, that's literally all. That's basically what you have to know about how this algorithm works. Yeah.
So we create a new vertex on the right direction.
Yeah, the vertex that the new vertex being made is this one. Yeah. It depends on where we randomly like it depends on where this point was sampled, and it depends on the step size. But once you have those set, then it determines which new point and edge is added. Yeah. Yeah.
Why would just this 2 point instead of just adding the vertex?
You can do that. Yeah. Again, there's a huge amount of variance of this stuff. So, if you want to, you can decide, well, maybe we should just continue in that direction. So let's just keep continuing. Yeah, you can do that if you want. In fact, I think that's what many implementations do. Like they keep trying to grow it. Yeah. Yeah. Question.
Yeah, when you sample the random tree configuration, is that in the task space or in the joint space?
All right, so when you when we're sampling the point, is it in what space or the joint space? You talked about something else first.
Yeah, like, is it like an X, Y, Z coordinate? Or is it, like joint angles that you convert to, like you randomize the joint angles?
Okay, so if you're trying to randomly sample a configuration, is it going to be in joint space or like some position or end effector space? Yeah, I think that's a good question. My first reaction is if you can go from one to the other, I don't really think it matters because if you have one, you can go to the other, basically. It might matter depending on which sampling method gives you the best like coverage of the space you're considering. Um, For this visual, we're just visualizing it as a 2D point, so you can think of it as both really because you can think of it as mostly position here because it's just points in a plane. Yeah, I think in general, maybe it would be in joint space. But again, I think as long as you can convert from one to the other, I'm not really sure the distinction matters too much. That would be my intuition. Yeah. You do have to make sure that the sampling kind of covers the space you're considering. That is important to make sure the tree is growing. So. Huh. All right, so when do we stop RT? So we can keep expanding the tree, right? But if this is going to be mostly for a single query, then you might as well stop when you sample a point that is in your goal region. Because if you have that, then you're basically done because by the construction of the tree, you've already got your path from start to end. Because we started the tree from the initial code, and then each time we expand the tree, you can have a pointer for each node that points back to the parent node. And then, but once you get that, you get your path, and that's what we wanted. And again, we only add the node if there's a collision-free path. So, yeah. All right. So how do you choose the step size? So why do you think this? I mean, this value step size, I feel like it's an important hyperparameter. So if you set it really small, then your tree will grow very slowly. And then each new edge is only going to bring you like a little bit further in some direction. And it could, cause the tree to blow up in size. Especially if the nearest point in the tree is very far from the point that is sampled, then you might as well choose a bigger step size so that you can try making more progress, towards that randomly chosen point. So, and again, you can also make this adaptive, so there's no need to keep a fixed step size for everything. So you can make the step size dependent on where you sample, basically. So it doesn't have to be fixed for the whole tree construction. You can make it vary based on your nearest point in the tree to the randomly sampled point. All right. So here's what the tree might look like after you run RT. Like in a 2D setting, you might have trees that look like this, where the different circular regions are optical. So like in the first one, there's no optical. In the second and the third one, there's optical, but like of different shapes and sizes. And then the bolded line, you can think of them as your path from start to end. And so, when I was looking at this, the first reaction I had was like, well, this doesn't look like a very efficient path. So it looks like you're going from like, especially the second one, it looks like you're going towards the center, and then you go back, and then go around, and it feels a little bit inefficient. But this is, again, this is an RT, basically. It's not a roadmap, so you don't run a graph search to find the most efficient path. You just stop when your tree reaches the goal. So if you want to clean up this path, you have to do post-processing, which in practice is what almost always happens when you run RT anyway. So the reason for these paths is just because of the nature of like which points got sampled and then how the tree grew and so on. All right, and then yeah, this is an animation of how the algorithm works. So you start with some initial pose and then you just keep going. And the one thing that you'll notice here is that RT really they nicely cover the space, right? So it's not as if you randomly sample and then you're stuck in a nearby local region. It actually fills up the space quite nicely. So that's an important property. It assumes that your sampling procedure sampled points that were like uniformly at random throughout the full space. But if you do that, then you get this type of tree expansion. Right. So I think another way, yeah. So if you want another video, yeah, this is another video. So this is actually from the guy who invented RTs. So he had this, like, I think that this was a talk that he gave at a conference. Just like I think they invited senior researchers to give like retrospectives on like, oh, 20 years ago I did this, and then wow, look at what has happened since then. So if you look at, I think if you look at 610 in the video, yeah, so Laval was the person who invented the RT. And if you look at, wait, how do I find 6 minutes? Yeah, like if you want another video of how the expansion works, it looks like this. So, there's an iterative process. Yeah, so he's gonna pick a point at random and then keep trying to expand them to fill some space. Like he's skipping some steps here, but you get the idea. And yeah, so I like the analogy of trying to drive towards each sample point, and then that helps to explore the full space. So this is similar to what you saw earlier, right? This is another example. Yeah. So if you want, you can look at this video, and it's a pretty nice retrospective. And then you can see things like, oh, I came up with the name of this algorithm from this, and that, and so on. All right. So again, there's many design choices when you decide how you're going to implement RT. So, if your step size, if it's too small, you might not grow the tree as much or as quickly. A potentially bigger problem is that your path might be very jerky because of the way that the tree was formed, and because you saw examples of that a few slides ago where I showed that the path from initial to the end was very jerky and it didn't seem very smooth. So that's why people try to do shortcutting. And I mentioned this figure at the end of last class, if you remember this figure where you have your original path, which is in a dashed line, and then you can select 2 points at random, and then you try to connect to them. This example is, I feel like this example isn't this example doesn't actually smooth it, like, it doesn't look smoother, but it makes it use fewer vertices. If you want your path to look smoother, then there are different ways you can do that. Some people try to implement like a spline where you make your path look more like curves instead of a, a, a straight line from one point to another, than a straight line from one to another. So those are different ways. There's many different ways you can post-process your RT, which is basically necessary for real-world applications of this algorithm. All right. And another point, another big point about RT, the sampling process is very important. You would want to make sure that your sampled points cover the whole like space. And when we talk about sampled points, what I don't mean are like the vertices that you add. I mean the points that you sample and then you try to grow the tree toward that direction. So that's the difference between points that are sampled and points that get added to your tree. They're not the same thing. And some strategy that people have used are, well, if you have different components that where your starting point and then your goal point are in, try to sample points in those regions, like, and then you can grow the tree in that direction. Other ways are that you can just have purely random, or you can have a combination of purely random in the C space versus samples that are biased towards the start and the end. I think the inventor of RT basically suggests doing like this bullet point. He suggests some like percentage that you can use. I don't know how you might have to tune that, basically. So are people familiar with the Voronoi diagram? So it's a type of emergent property that emerges from the RT algorithm. So the way to think about this is that this is a Voronoi diagram where you have a bunch of points and then you color the regions of it so that if the region is, if there's a colored region, then for all the points in there, the closest point to it is like, it was the point that is like, that defines the Voronoi region. Yeah. So what happens is, the boundaries of these are the boundaries of these are where, like, for all locations on the boundary, they're equal distance to the corresponding Voronoi point. So you have a bunch of points, they each define a region, and then the boundaries are like, equal distance from one to another. Yep. So this is not like, there's nothing in the RT algorithm that tells you to, bias points so that you can, like, I guess, shrink the Voronoi region. It's just an emergent property. And what the RT will do is basically it'll try to explore more in regions that, I guess, where they have a bigger Voronoi diagram, so that it can increase, it can reduce the distance from any point in the workspace to the tree. Yeah. So if you look at how the sampling process works, the probably biggest like advantage of RT versus what we call a naive sampling is that the naive sampling will give you something like this in the 2D region. It looks like a hairball thing. Yeah. Whereas the RT will give you a tree that covers the space pretty quickly. Yeah. So again, just to be clear, like, what's the reason why RT is different from the left? Like, I gave you the steps for this. These steps are for this. So. Yeah, so why did RT not result in the left diagram? I mean, if it resulted in the left diagram, it wouldn't work, basically. You can't have a planning algorithm that only gets stuck in. Yeah. Okay. Yeah, what?
Was that?
Can you expand upon what you're saying? Yeah, that's okay. Yeah. But what does RT do different, basically? Yeah, because RT does something different from the left, basically. Yeah. Yeah, maybe. How about yes? Yeah.
Step size hyperparameter that causes when we send it, we go to vertical line and greater step size so it stands out.
All right, so the size of the hyperparameter, like the step size, that's part of it. I think the bigger reason is it sample target uniformly in the space, and then the tree tries to grow towards it. So it's less about the steps. You can still have a small step size, but as long as you're sampling points that are like far away, you can still like grow towards the point. But what's going on here is you start in the middle, you sample near a node, you pick another node at random, you sample near it, you end up staying in the middle. So there's nothing about sample a point anywhere in the region and then try to go towards it. That's the difference between this and RT. Okay. All right, so as I mentioned earlier, there is a lot of variants of RT. So they usually they're named something like, adjective or verb dash RT. That's usually how the naming works. So this one is a variant called transition RT. So I guess instead of using it's not just using like a step size and then you run your collision checker. What this might do is it tries to use the concept of like a metropolis test. And if you're familiar with statistics, like sometimes you'll you sample something and then you accept or reject it. And this one is a variant where you try to sample some target point, you try to go to that point, and then you accept if you use a transition test to accept or reject, basically. So the transition test tells you whether it's good to keep expanding in some direction. And the main difference, the main like use case is whether you have if you have a cost function or some kind of environment where you can express it as like a set of like values or saddle points. Like you can think of this as say like a 2D terrain with a bunch of hills, and then you try to keep growing the tree in region where like there's valleys or like local minima, and then that'll help get from like one point to another in areas which have high cost. So this feels like it's kind of like a more relaxed or a variant of your normal collision, where instead of having obstacles that you cannot go after or like that will always collide, you can technically go to anywhere with some probability. And the region with lower cost have higher probability of going toward. Yeah, question?
Have you assumed that this is probably a greedy approach?
Can we assume that this is
Greedy approach.
a greedy approach? Hmm. I I'm not, I guess I don't think of this as a greedy approach. I think of this more as a probabilistic approach. So it's like you grow the tree according to some target and with some probability. And the probability is based on the cost difference between where the node is at versus where the target is. And the cost is expressed as the height of the like map. Yeah, so the easiest way to think of this is if you're a point robot operating in a navigation environment which has different like height. So the higher it is, the higher cost it is to go. And there's a transition test which you have to sort of pass in order to consider accepting or rejecting the sample to grow the tree. And then what this equation is doing is basically saying, if you're going from one point to another in this kind of environment, if you go downhill, you're always going to accept. If you go uphill, you accept proportional to the probability or the slope. So if you go from one point and then to another, which is extremely high, then the probability is much lower of accepting it. So, and then yeah, so you can look at this paper if you want to know more of the detail. It's a pretty readable paper, and then there's different parameters like K and T. Like if you increase the value of T, you sort of like spread out, you sort of flatten the cost map. So that's what the term temperature means. So temperature is often used not just in this, but in other contexts. Like, even like ChatGPT has a temperature parameter. Like if you try tuning it for your homework, then you increase the randomness if you increase the temperature. So yeah. Again, you can use it for your homework, you just have to cite it. So. And if you want a video, it looks something like this. Yeah, so the user has a mouse, and then they're trying to click to show the start and then the end. Uh, uh, so again, to just at least the way that I like this, the way that I have intuition about this is you're like a point robot operating in a 2D environment or a 3D environment where they're not really true optical, but they're like optical with some probability. Like that's basically how I think of this thing. And then you try to find some paths in regions with low cost, and then usually what will happen is they find some path that avoid the high region of this cost area. So uh, oh yeah, there is another like this a variant of this is within one of Stefanos' papers. So if you're wondering I don't want to do 2D navigation, I want to do like work with the physical robot on, you can look at this paper for more detail. They do a variant of RT for this. And the objective here is that is to reach into this tree and to reach the line. I think it's line. And the leaves are permeable optical. So they're not like optical that the robot cannot touch at any cost. Like the robot can touch them, and then it just might be, maybe there's going to be maybe it's just going to be higher, a little bit higher cost if it touches the lead, but it's not so expensive that it prevents the robot from, touching them at all. Yeah. So I think if you want to know like more details, I think one of the TA, the Heja, has also experienced working with RT for this robot before too. Yeah. Oh yeah. All right. So completeness and optimality. When is an algorithm complete? If there is a solution, the algorithm will find it. Otherwise, it reports failure. Probabilistic completeness means if a solution path exists, the planner will eventually find it. What does eventually mean? As if the number of samples in a sampling-based motion planner, as the number of samples goes to infinity, the probability of finding the solution goes to 1. I mean, if you have to have a super high number of samples, then maybe it's not good in practice, but I get that it's at least good to know if an algorithm is probabilistically complete. All right, probabilistic optimality. So if the number of samples increases to infinity, do we get arbitrarily close to the optimal solution? If yes, then it is probabilistically optimal. Are RT probabilistically complete and probabilistically optimal? So think about it for a bit. Hmm. I think the answer is yes for both. What do you think? All right, nobody wants to disagree. Hmm. We can be here all day if you want. I mean, like, do you have like any intuition? Like what do you feel like these mean? Hmm. I'll give you a few more seconds, and then we'll go through the slide to explain them. All right. More concretely, an algorithm is probabilistically complete if for any robustly feasible motion planning problem, that is, if a solution exists, then the as you increase the number of samples in the sampling-based motion planning, that is if the number of samples in that tree, if that increases, or no, the number of sample points basically, which is different from the number of vertices in the tree, because the vertices grow in the direction of the sample. Then the limit of as n goes to infinity, probability of algorithm returning a solution is 1. Right. So if you think of RT, they go and they massively explore the entire space of the configuration space. And so if a solution exists, if in theory there's any path from like start to the end, then RT should be able to find it. Right? It might not find the right, it might not find the right one, but it'll find one. Right? Yeah. Yeah.
Stop when it is impossible, because if
So what we talked about when we decided to make RT stop, right? If you're in the goal region, you just stop. Yeah. If a solution does not exist, well, then it can't, no, you can't just stop, right? I mean, you would have to have some kind of maximum number of samples you're willing to try before you just decide, call it a day, and then it's just not going to find one. I mean, you're doing a sampling-based algorithm, so you have the number of samples. That's basically the main thing that you can tune. Like how often, how long do we want to sample it? Yeah. I, asymptotic optimality. If you let this be the cost of the best path from running RT n time, that means you have the number of samples, n, and C star is the cost of the optimal path. So if you want to think of the cost, just think of it as like, the distance from point A to point B, like just a simple sum of the distances of the edges, right? As you sample more nodes, the probability that, that your best path is more costly than the best cost will go to 1. So what does this mean? So what this equation means is that as you increase the number of samples to infinity, you actually do not get close to the best cost, right? Make sure you understand what this equation means, because this is actually a very important thing. And the intuition is that when you have the tree expansion, you're sort of, I guess, the algorithm then ends up trapping itself by disallowing new paths to emerge, unless you do things like post-processing, in which case that's a different story. But the vanilla version of RT is going to trap itself. Like it tries to grow the tree, but as it keeps going, you've got your pointer that points to the parent, but you end up like not being able to change that because you're stuck from your start to all the points that led you from start to the next node to the next node to where you are. So yeah, this is the intuition. Like RT will mainly find a feasible path quickly, but you're not going to get the optimal one. And so the very famous paper, this is a very famous paper, and then they had this big summary of a big summary table that showed like which algorithm was probabilistically complete, and then which one had asymptotic optimality. So I think for the purpose of this, you don't need to know like everything in the table. Like I think the most important thing is to know that probabilistic roadmap and RT are probabilistically complete. So if you run it long enough, it'll find the solution if a solution exists. But they do not have asymptotic optimality. So that's why you have yes and no for these two. And then these other two, there are other existing algorithms. So this one at the time it was like 2010 or so. Then like the beauty of this paper is that it showed that PRM and RRT, which were like state-of-the-art algorithms, they're not asymptotically optimal. And so they proved that, and then they showed this other algorithm, and then they call it PRM star and RRT star. And then they showed, oh, those algorithms are in fact, they're asymptotically optimal. So that's why in practice, you'll first learn about motion planning by using RT, and then when you go to your like research project or like in industry, you use RT star. That's how it works usually. Yeah, so in my lab, we're trying to do getting some robots to do basic motion planning, and my students are using RT star. Yeah, and then you see like how people like name the different algorithms. You have like something dash RT or something dash PRM. Like that's how people name the algorithm. I think this is a good time for a break. So maybe like a 5-minute break, and then just look at this table and maybe look at the paper if you want. It's about 70 pages, so just take a look at that if you want. Actually, 76 pages, I think. depends on the font size that they use too.
Like I came across RT star smart as well. Like, is it different? Researching for this.
There's a
RRT,
there's a ton of variants of RT. Like I don't know them all.
Oh,
yeah.
so like what parameters do they change normally?
They probably change how they sample they probably change how they sample where to grow the tree and then how to rearrange the tree. Like how to prune away the tree and then restructure it. That they probably have different variants of that. That's probably how they do it. Yeah. Yeah.
Sampling technique that I've worked before. So are you familiar with like the Rudevi, how a Rudevi works and how the Rude sampling is done? The what? Rude sampling, the casino one,
Rolex sampling?
like how roulette is done. So based on that,
You know, like the gambling?
no, but like based on the concept of roulette, sampling is done.
Yeah.
In optimization problems usually. So, like, have you heard of something that is some of that sort done in this? Like,
I
have you heard-
haven't seen something like that for this. I mean, I'm sure someone has tried it, but I haven't, like, I don't know anything explicitly about like that called a roulette, like, thing. Yeah. There's usually someone who sits next to you.
Yeah. But his car. So it's now a good time that he's unfortunately.
Watch the.
Yeah. He gives quite his best to argue with this reasonable driver, but
All right, one more minute. Some pages are easier to read than others. All right, let's get started. All right. And by the way, if you want, like when you read these types of papers, I think one thing that can help is at least reading the abstract and the introduction. Like you don't have to read the proof or the derivation. Like I often do that for a paper. Like if they're not like directly in my area, I just skip the detailed proof and then I read the abstract and then the introduction, which tells you like the background material. And then if you read this paper and you look at section 1, that'll tell you what you need to know about what they did, basically. And then if you want to run the algorithm, someone has already come up with a library for these algorithms. So you could just run them. All right, here's another variant of RT. So anytime RT. And that's literally the title of the paper, though, anytime RT. So again, it's like a variant of RT is like your adjective or verb dash. Well, actually, in this case, they don't have a dash, but they have RT after. So you find your suboptimal path quickly, which you get with RT. You just get your fast, go from the start to the end result, and then you improve it over time. So you produce your initial path, then the next run you try to stop when your revised path is of lower cost than the original one. And so you can do that. There's different ways of doing this. So you can keep old tree, like what you can do is you can think of running RT and then you run RT again from like the root node or whatever. You can keep old tree, but the fact that you're keeping your older tree, like that was the original problem with RT than not being like asymptotically optimal. You can try rebuilding the tree from scratch. And then, but that also feels like you're running RT many times. Like if you run it 10 times, and then you take the minimum of those 10. I mean, you can do that, but it seems very inefficient. And so what the summary of what that paper did is what that algorithm proposed is this heuristic to consider like a subset of nodes from from the previous RT run, and then you keep that when you run RT again. So there's different ways of you run RT, and then the next time you prune away parts of the tree, then you just run RT again with those set of nodes in edge. Yeah, so people have come up with all types of heuristics for like pruning and improving paths across different sampling runs. All right, a bidirectional RT. If there's any variant of RT that I think is important, it would be either this one or RT star. Yeah. And in fact, if you look at this, it says, homework 5, RT2. So look forward to homework 5 then. So you have, so you have your start node and then your goal node. And the key idea is instead of just starting from one initial point, and then you just grow, you try to grow from the start and the end, you grow both of them, and then try to connect them. And because of that, you might require fewer samples. Empirically, people have found that that's the case because it feels like, if you know where you want to go to, you might as well like grow a tree from it instead of, just starting from instead of just expanding from your initial point. So here's the visual. Yeah, so here's the visual of your homework 5. So, this is like a start, this is the end, and then you just keep growing the tree, and then the box-like things are obstacles. So, and then you just alternate which tree you keep growing. And this is how if you plot it and animate it, it'll look like that. And at some point, it'll connect. Yeah, it's again sampling-based algorithm, so sometimes it's not going to grow. It'll grow in many different directions, and then it found a solution. So, and if you want like an implementation, like this is one example of an algorithm from another paper that discussed this in the context of like how do you do inverse kinematic to go from like your start pose to the end pose, and then you have like the two different poses, and then you grow the target backward, and then you move the initial pose forward, and then try to connect them. So you can look at that, but I think there's another algorithm from I think the textbook that looks that's a little bit easier to understand. So if you look at the top diagram, this is how you add a node to a tree. So you have your your queue and then your randomly sampled point. So remember, right, the point that you sample is not what you add to the tree. You're only growing in that direction. Again, that distinction is really important for the RT. So you have your queue and then your step side, and then you grow in that direction. And then you added it with a collision-free, if there was a collision-free path. Now, the way to merge the tree, imagine you have your initialization and then your goal pose. And then those are two trees. You grow them backward. You grow both of them. And QRAND is the point that you sample, and then you merge it if it's like within some distance from, to both trees in some sense. And then if you have that, then you automatically have merged the trees. Yeah, so I think what they do is, so the algorithm will choose a randomly chosen free configuration. It'll try to extend it, so it'll try to extend the first tree. If it's not nil, that means it could expand. Then you try the second tree, so that's T2. But you try to extend this. And then if the points are the same, then you return that they're merged. And then the reason why they have a swap is because they're assuming that you do the first sample from like tree T1. And then this is just a technicality to try to switch which tree you will start sampling from. So, any questions on this thing? Yeah. Okay. Yeah. And if you also want a little more intuition, then maybe just think of this diagram. So if you had no obstacle and you could try to grow the tree in basically any direction, then if it's unidirectional, then assuming the same distance from your start to the goal and the start to the goal here, what's the relationship between the total area of this and the total area of this? Yeah, like you can do some geometry here, but it's basically like, the first way will try to grow and it may take more exploration and more tree growth to get a solution versus the second case. Yeah. All right, multi-directional RT. Again, I keep telling you that there's a lot of variance. So, I mean, what's your reaction to this? Like, what do you think is going to happen here now? We just talked about bidirectional. What does multi-directional mean? Is there any reason why we had to limit to 2 trees? Why not just do 3 trees? I mean, if you want to do that, sure, you can do that. I mean, it's sampling, all right? And then if you can connect, you can still connect trees using the same heuristic, like, your sample point, and then if it's close enough to the different trees, then, you're all good. So what this diagram is showing is there's different shapes, and then the solid contours are optical. If you have Q, the initialization here, and then the goal here, if you have RT and growing from just one tree, it might get stuck and it might get stuck based on the shape of the optical. B is the bug trap example. So what this means is that if you have your initial pose that's inside this bug trap versus the goal pose, which is outside of the bug trap, then if you only go from the inside direction, it might be harder. You're familiar with what a bug trap does, right? So. So does everyone see why for B it's better to do a bidirectional RT than a unidirectional one from the point from QI? Yeah.
Yeah.
Maybe it doesn't have to be that big, right? So this is a bug trap. So if you try to grow from just this, then you have to figure out how do you go through that narrow corridor, right? So if you look at any point that is within the corridor, if you have a circle around it, then the line of sight is going to be greater for the outside RT. So that means if this is the sampled point that we sample for RT, then there's more points on the outside that have a line of sight visibility to that point. But if you're inside, then the optical will block it. Maybe let me make it a little bit bigger. It's a little bit hard to see. So So all of these points have a line of sight connection. So they can grow in that direction. But if you have points here, you have to be like here to have line of sight connection. So that's the intuition for why it's easier to grow the tree and go through the optical from the outside than the inside. I mean, real bug traps are more sophisticated than this, but this is the main, like, this is how I get intuition on why this works. I mean, you might have different intuitions, though. Yeah. All right. So any questions on A and B? What about C and D? How do you do, yeah, so for C, it's a double bug trap. So you probably need like 3 trees. What about D? How do you do D? I'll give you a couple seconds to think about it. Yeah. Yeah, what?
Maybe we need to start at 7 instead of 3.
Maybe you need what? 7?
Yeah.
Wait, 7 trees?
Yes, 7 start point.
Wait, so you want 7 starting point?
Yeah.
Oh my, okay. That's a lot. Yeah, but maybe you need that. In the textbook, if you read the textbook, it says this problem is hard even for multi-directional RT, and then period. It doesn't say anything else. Yeah. Yeah. Question in the back?
I think 5 should be enough, given 2 inner loops are there. And 1 outside could be like that. As it's open, it's pretty much easy to have 1 outside.
All right, so about 5. So maybe one outside of everything. One of them in here, then one of them in here. That's 3.
And 2 are already there.
Yeah, so yeah, that's 5. And maybe you could probably even get away without using the inner tree, because really it's actually easier to go outside than to go like inside to outside. But you could still have the trees inside. Yeah. All right. I mean, 5 trees is still more, Yeah. But yeah, if you look at the textbook, it's just this is hard even for multi-directional RT, then period. Good luck. So, Hi, time varying planning. So what we're now going to talk about are different variants of the planning framework. So so just like RT had many different variants of it, there's many different problems that you can formalize. There are many different frameworks. So time varying. So if you might remember that when we were talking about the sampling-based planning, we just assumed that the optical and the goal, they were just static. But in reality, there's many different cases when your optical and maybe the goal can move, right? So when your opticals are moving, it gets harder. So yeah, so a good example is the robot parkour, like like in many different video games, you're trying to go from start to end, and then there's like optical, like like fences that try to fence you in and then go out, and you have to like time your movement to go through them. That's kind of like what's going on here. So you try to like navigate in cases where your obstacles are moving. So one way to do this is to have your state space be x equals qt. So t is the time component, and then q is your normal like state space, joint angle stuff. So you'll see that many of the different variants that we cover, they can be approached by taking your state state space and then adding more terms to it. So you remember from earlier you had like augmented state spaces for the Kalman filter, and yeah, so you remember that midterm question and stuff like that. So you have augmented vector. That's kind of like what's going on here. Your optical regions are, they're defined as all your combinations of the robot configuration and the time, such that the intersection between the robot and the optical is not equal to the empty set. That means it does exist, so there exists some type of intersection between the two. So there's some optical region there. Right. Yeah. All right, and there's some different assumption that you can make for this. So usually if you assume that opticals are rigid bodies, and then it's easier in some sense to model their movement. So instead of things like deformable things, which are much harder. So you can think of like deformable opticals, like lava that flows and whatever. Then you have to like time the robot to avoid it. That kind of stuff. No. Yeah, and then this time the goal is to compute a continuous time monotonic path. So again, remember that we often write tau from 0 to 1 because you can normalize your time to go from 0 to 1. And then the path must at every single time step map the robot to be in the free space. And then what did this say? So for any S1 less than or equal to S2, so those are the inputs to tau. So those are just like values between 0 and 1. This thing which must imply this thing. So if you're earlier in the path than later, it just means your time must be, the first time must be less than or equal to the second time step. Then yeah, your tau will map to Q1, T1, and then tau S2 will map from Q2 to T2. Yeah. So this is just a way of formalizing the notion that you need your sample to be such that, if you sample something and then at the beginning of the trajectory, it needs to have a smaller t value. This is just a way of like formalizing it. All right, here's an example. There's a convex polygonal robot that translates in R2 and a single convex polygonal optical O. Now, in this example figure, we're just showing the robot as, again, a single point math, but you can also think of it as like a polygonal robot. So what this is showing is T1, T2, and T3 are different time slices. So you can think of this as, the space, like if you didn't have time, you would just be looking at like a 2D configuration space. But now you have time, so you have to consider a third dimension. So time, so this is how it looks. So time will move in this dimension. X will move like towards the page or towards the slide. And then Y will point upward. So this figure is showing 3 time steps. So at every time step, you take your slice, and then it's showing the 2D slices if you move them like in front of us. So does everyone see like how do you get that? Yeah. Because like at time 2, the optical is like moving. And so when it moves, you have to, it'll change the location from here to here. And then from here to here at the end. Then our goal configuration is just going to be some kind of point in the 2D plane. So it might be over here. Yeah. Yep. All right. So again, any question on the figure? The figure just showing an example of how you might think of a setup where they're like a convex polygonal optical that moves, and then at different time steps, it might move in a different direction. Because that's why we call it like piecewise. Yeah. All right. How do you approach these problems? Like, how do you solve? I don't like using the word solve, but if you want to use it, though, how do you solve this type of problem? So the way that you could do this is by adapting the various sampling-based algorithms that we have already covered. Because if you think about it, your samples are still going to be like just sampled points. So you can only just try to sample them and then try to connect one point to another. And then you stop, you don't connect them if there's a collision between them. But what you also have to do here is to make sure that you cannot connect two samples if they move backward in time. So again, whenever you're doing your sampling, instead of sampling just X coordinate and Y coordinate, you're sampling X coordinate, Y coordinate, the time. Yeah. I think it's easier if you discretize the time. So you have like 100 different time steps to sample from, and then you could just pick one of those 100 values for every sample. Yeah, and then this is like a pseudo metric. So think of rho as your normal like cost function or some kind of local planner that tells you, can you go from Q to Q prime? Can you go from that configuration to the next configuration? Now you just augment it with rho X of X the next prime, and then it'll be, I guess it'll be 0. So it's like a no cost if your two configurations are the same. I guess there's like no cost if it's referring to the same configuration in some sense. Now it will be infinity if they're in different configuration and the T prime is less than or equal to T. So because we need T to be before T prime. So I think that's what this is trying to do. So you have your cost is going to be infinity, so you cannot connect X and X prime in your graph, or in your tree. Yeah. All right. Do you have any questions about that pseudo metric? Basically, if you think of this abstraction, you just use that type of cost function and then just run normal RT with that. Or you can even do something like a vertical cell decomposition. So we talked about that last class where we talked about like a cell decomposition, which assumes that you know the geometry of optical. Then you could try to connect, draw a vertical line, try to sample like your point and which are centroids of each line or each trapezoid or triangle, and then you kind of connect them. You can extend that to 3D. And then you will want to make sure that you have to enforce bound on the robot velocity. So if your robot point here is suddenly up here, what did that mean? Like suppose what happened here is that this point moved up here. So I find it easier to think about that question by looking at the 3D diagram, but then looking looking in to the side in some sense. So I'm looking at the XY plane in front of me. Because we're looking at the YT plane. So we're looking at the YT plane. I'm looking at the XY plane. So I find it easier to think about that like that. So no, if your point here is like way up here, then that means your robot has like quickly moved. In this case, it's upward with the higher Y coordinate, which means it got some velocity. It got some velocity, and the shorter T1 and T2 are, the quicker the robot moved up, which probably means it's usually not as good. You usually don't want your robot to move too quickly for safety reasons and whatever. Hi, planning in discrete and continuous space. So this is another type of framework. So we talked about time varying planning, and then this is like a discrete continuous planning. And the motivation is, well, many times it's easier to think about something if you have a mix of discrete versus continuous. So one example would be if you have a robot manipulator with a parallel jaw gripper, which means you have like a discrete open gripper or closed gripper action. Or you might have, your door, like a door which can be open or closed. You have your vehicle, which can be in different gears and whatever. So those are discrete things. And then you can combine them with continuous values by, just you have to combine them with continuous values for those things that are better expressed with continuous values, like joint angle. So what happened is you have the state space, which is like a Cartesian product of your normal configuration space and a finite set called the mode space, which is your discrete space. The space of different settings you have for your discrete variable. So what this diagram is trying to show is trying to visualize these spaces having like layers of C spaces that are indexed by the mode. So these are the different modes. So the robot might be able to go from mode 1 to mode 2. Once the robot is at mode 2, it could go to mode 3 or it could go to mode 4. If it's at mode 3, then, well, I guess it's stuck there. If it's in mode 4, it can go back to mode 2 or it can go to mode 3 where it gets stuck. Yeah. And for every different mode, every mode might result in a different configuration space. Because if the robot changes the mode, maybe the optical might have to change. So imagine your robot can change its size. So if you have like your vacuuming robot, that round robot, then maybe there's a mode where it's a default size, but it can shrink if it needs to go into like a tight corridor. Then that means your C spaces will be different. So I don't know if a robot exists like that actually. So maybe that's something for someone to try. Do you know what I mean, right? Like you have your Roomba, like the vacuuming robot, which is a circle, and then I want it to shrink. if you need to fit into something tight. But normally you don't want to be in that because it'll be less efficient to vacuum in a bigger area. But sometimes you need a tighter, you need like a smaller robot. So sometimes we call this the hybrid system framework, where again, it's the same technique. It's basically the same technique as the time varying thing. You just augment your state space, right? So your state space is Q cross M instead of being cross time as before. So X equals QM, where Q is like the robot configuration space, and then M is a discrete set of modes. So before we were talking about time with QT, then here we're talking about Q and M. So then yeah, there's this optical region OM that depends on the mode and the robot, right? So again, it's mode dependent, just like before it might have been time dependent. Here it's going to be mode dependent. Then each state will have a finite action space, so U of X. Then you can have a mode transition of FM, which takes you from your state with some action, and then it will result in some kind of mode. And then the state transition is going to go from XU to Q of this thing, which is over here. So when you do your mode transition, this thing will only change the mode. So it's not going to change the configuration, right? So the change in configuration happened from F. Yeah. So again, FM is going to be a subroutine of some sort of F. So yep, and then you have your initial state and then the goal region. So given the prior framework, our objective will be compute a continuous path of tau such that for every single time step, you map the robot to something in the free space without any collision. Then you also compute an action trajectory, sigma, such that for any given time step, it'll map to some action that takes the state and the action, and then it results in a mode. It might be the same mode, but it'll give you a mode. So yeah, so the changes in the mode depend on the action taken by the robot. So that's why you cannot associate any like sigma with a path. Like they go together. Like you have to what action was implied to introduce the correct mode transition, which might then determine what's the free configuration state given that mode. So these things are very intertwined. So again, this is a different type of framework. To me, it's kind of similar to the time varying one in the sense that you still have your augmented state space. Then you have to consider like your normal configuration plus something else. Then that other thing like time or the mode can change the optical or the configuration space. At least the free configuration space. It could also change the normal configuration space itself. Especially if the robot can change its size. So. Yeah, so here's a very simple example. You have two modes, open and closed, right? And now what is O? Well, we thought what O was. O is your optical region that depends on the mode M. So you have O of M. this O is like representing the optical. So when you open the door is still an optical, it just changes where it is. So like you cannot go from like over here directly, down here because the door is now in the way. Then our state space might be, XS, which is your starting state, and then the mode, which is closed, and then your goal state might be QG, which is your goal configuration of the robot, also combined with being in the open mode. So maybe your starting state is here. The goal state is here, right? The goal configuration of the robot. And then you can run your normal like sampling-based motion planning thing where like maybe this node was just added to your tree, to your RT. And then you might have an act like this might include your action to actually open the door, right? So if the robot is like close enough to the door can like do an opening action. So, so remember there's an action here, like each state has a finite action state that include, do nothing, but also in this case, open the door. Yeah, and then you just, again, you can try to connect your path, and then, this will give you, I guess, your path from RT. It's just that you have to consider the abstraction of having another like component in here, which is the mode. So here's another example. So does everyone know what polyurnia means? If you look at the textbook, it says it's like a special thing in the country of Poland where like you have security guard, and it's like something that helps the guard manage their key. But I don't have any Polish ancestry, so I'm not sure. I've never heard of this term before. Yeah. All right. So I guess nobody really knows what this means, but yeah. So this example is referring to the polyurnia, which is this region in the upper left. If the robot is there, then it can get a key. It can get the key to either the first door or the second door. And if the robot is close enough to the door, it can try to open it, and it'll work if the correct key is there. So do you see why the optical region is mode dependent? Because if you have your key to door one, then door one is not really an obstacle in some sense. In some sense, the door is not an obstacle for the robot to go through it, go through the space from the door. We're assuming that there's nothing like the door opening and then making another obstacle. Maybe it's like a sliding door or whatever, or like some other like some secret room door where you have like invisible doors that then you can have a key and then it opens up. Yeah. You see though that some like airport lounges where you have like secret doors too. So yeah. All right. So if we asked you like how many modes are there, then you can, so the number of modes is subjective. You can argue that the mode count is something subjective, and yeah, you're correct on that. Like one reasonable interpretation here that there are 12 modes because you have 3 different combinations of the key for the robot to have. Maybe it has no key, it has door 1, it has door 2. So you can argue that maybe there's 3 modes for the key, maybe 4 modes for the state of the door, and then you combine, you have all their combination, which is 3 times 4, that's 12. So if you're trying to design this, you can make a credible case that, well, there should be 12 modes here. You might disagree with this, but you can always pick a different mode count if you can make a compelling enough argument that, maybe your solution should take into account just those modes or whatever. So, yeah. And another exciting one was, like, I mentioned this earlier, but you can also consider like a reconfigurable robot. And this is a robot that can change its shape, right? These are the things, really. And even robots that you don't think can change their shape, they can often change their joint angle. So they would end up changing their configuration anyway. But at least in this case, you can think of the robot as, being either in an elongated pose or a compact, like square-like pose. So if you look at this figure 7.13. What did the robot have to do to go from the start to the, like, maybe the start is to the bottom left and then the goal is to the far right? Can the robot stay in one mode and then do it? What if it stays in just the elongated pose? Yeah,
So.
yeah, basically. So yeah, maybe actually I think my phone is like the right width. So we have like you try to go from here to here, then it gets stuck. Yeah, my phone's a little bit too big, but you get the idea, right? And you also see why this is like the free space, right? Do you see how we get this free space? Because imagine the robot stays elongated, then it cannot move through this. So this is something to think about. Like, think about your robot being a single point mass. Then if it's a point mass, that means you have to make your, like, you imagine it as expanding your optical. So I think we talked about that in a few other classes where, like, your robot is a point mass, but if you want to make sure that your robot is like avoiding optical by some amount, then you have to expand the optical, and then the advantage of all this is that it reduces your analysis to just thinking of a robot as a single point. So here when the robot reconfigured, this space will change, and then this will express the, I guess maybe the coordinates of like where, like, roughly the center of the robot might be, or like the bottom right coordinate. Actually, I do think it's the bottom right coordinate because it's not this is not corresponding to the center of the robot, but the bottom left point. Yeah, I think it's the bottom left point. Yeah. Got it. Hopefully that's clear. Like, you just think of your robot as like a single point for making the diagram. Right, so today we covered RRT, including the bidirectional variant. So if there's nothing to take away from this, like, there is a ton of RRT algorithms, but the most important ones are RRT, bidirectional RRT, and then if you're implementing things like RRT star. Those are the three most important ones to know. And then we talked about different frameworks like time variant planning, continuous discrete planning. Coming up next week, we will talk about task space region, which I think is your lab 4. So I'll see you next week.